Air System, Lesson 1. In the previous lessons, you have learned that air is used to create power as it passes through the engine. Air inside the engine is also used to control the fuel schedule, to cool engine hot sections, to form oil seals, and to prevent surge. When you have finished this lesson, demonstrate your understanding of material by taking the progress check on the following performance objectives. First, identify 3 of the supporting air systems. Second, explain the function of 3 of the supporting air systems. Third, identify the maintenance to be performed on each system. Here is your instructor.
Let's begin our discussion of the air system by reviewing the flow of air through the engine. Air enters the engine through a 360-degree path formed by the air inlet muff. Air enters the compressor and is compressed as it flows to the aft end of the engine. The compressor air then passes through the diffuser and either into or around the combustor. Hot air and gases exit the engine as they flow between turbine blades and out the exhaust bellows. The air system provides a PCD signal to the fuel control valve, provides cooling air for the engine, prevents engine surge during the startup cycle, and provides pressurized air for the oil seals inside the engine. The supporting air systems are the PCD control and indications, the turbine cooling air, the oil seal, the bleed valve, and the variable vanes. In this program, I will explain the PCD, cooling air, and bleed valve supporting systems. Now, you learned in a previous lesson that air pressure is the greatest at the diffuser outlet and is labeled PCD. The PCD control indication system bleeds air from the diffuser outlet and uses this air pressure to perform 2 functions. First, it provides a PCD pressure signal to the gauge on the engine gauge panel. PCD pressure is a primary indicator of engine performance. You may recall the charts from an earlier lesson that compared PCD with load and inlet air temperature. These charts, along with your PCD log, can help you determine when the compressor needs to be cleaned. Operating personnel should keep a log of PCD indications from day to day, comparing one day's figures with those from another day under similar conditions, which will indicate deterioration of engine performance. Second, the PCD system provides a pressure signal to the engine fuel control valve. This vital engine control link was described in the fuel system module. PCD pressure supplied to the fuel control valve increases with engine air production during startup. On closer examination, we find that as compressor speed increases, PCD pressure also increases. This increase in PCD pressure is transmitted to the fuel control valve, which makes proportional adjustments in the fuel schedule during the startup sequence. The PCD signal to the fuel control valve is supplied via a 3/8-inch line connected to a box on the engine bearing support housing. As you might imagine, if a leak developed in this line, the PCD gauge and fuel control valve would receive a false low signal. Depending on the magnitude of the leak, this drop in PCD pressure would prevent the engine from lighting off, or if the engine did light off, it might cause slow acceleration. In any event, the engine could not carry a full load. Maintenance of PCD system is limited to PCD gauge calibration and periodically removing and blowing out the lines. If the engine is started up and shut down often, the PCD lines will collect condensate. The lines heat up when the engine is running and cool down when the engine is shut down, causing vapor to condense and accumulate. Periodically, a PCD line should be disconnected at a low point to allow accumulated condensate to drain out. Remember, if any part of this line is disconnected, it must be properly secured to prevent leaks. It is a good idea to check this system for leaks the next time the engine is started if it has been previously disconnected. The PCD lines are very hot and should be handled with care to avoid injury. Now, in an earlier lesson, we mentioned the extreme temperature of the gases entering the turbine section. To assure the efficiency and long life of this section and other hot parts of the engine, air is used for cooling. The turbine cooling air system operates inside the engine, cooling vital engine parts during operation. Let's take a look at our cutaway model. Turbine cooling air is routed internally through the engine. Air is bled from the 11th stage of the compressor and the diffuser outlet and directed onto the turbine nozzles for cooling. The exhaust gases rush out of the combustor and into the first stage nozzles pictured here. You may recall that the first stage nozzle, like the one I am holding, is the hottest piece of metal in the engine. Cooling air that cools outside of the combustor housing is directed through this connection point on top of the nozzle. This air cools the inside of the nozzle and the trailing edge as it leaves through these orifices. The turbine cooling air system begins and ends inside the engine. It requires no operation or maintenance action by you. Another supporting air system that is internal to the engine is the oil seal air system. Unlike the cooling air system, the oil seal air system may require troubleshooting and maintenance by you. The oil seal supporting air system prevents the leakage of lubricating oil and forces excess oil back into the tank. If the oil were to leak, contamination would occur, causing a loss of power, extreme temperatures, and a decrease in engine life. Let's take a closer look at the construction and operation of an oil-air seal. The labyrinth seal consists of a series of soft, razor-sharp teeth aligned against another piece of metal. These teeth are made of soft metal to prevent them damaging the other parts of the seal. Oil is on one side of the seal and air is on the other side. As the air flows through the compartments of the labyrinth, the pressure drops and velocity increases. The high-velocity air escapes from the labyrinth, returning excess oil to the oil tank. The turbine engine has 4 labyrinth seals operating on pressurized air. The first seal, located near the cold end of the engine gearbox, is the output shaft seal. The second seal is the compressor rotor forward seal. The third seal is the compressor rotor aft seal. And the fourth seal is the turbine rotor seal. Oil tank air pressure is very important for the effective operation of the seals. If the tank vent is not sized properly or is restricted when installed, a back pressure will develop in the oil tank, reducing the effectiveness of the seals. Normal oil tank pressure should be less than 25 millimeters on a water gauge. Oil tank pressure should be measured and recorded when your engine is new. Subsequent readings can be compared with the initial reading for an evaluation of engine seal problems. Loss of power, extreme engine temperatures, and decreased engine life can be prevented by prompt replacement of damaged seals. It's a fairly simple task to diagnose damage to 3 of the seals. Well, let's take a closer look at the package itself. For example, if oil is leaking from the end of the gearbox, the output shaft seal is damaged and should be replaced. A vent hole located on the other side of the reduction gearbox can help you diagnose problems with the compressor rotor forward seal and the compressor cone seal. Normally, air is blown out of this hole. If you should notice both air and oil being blown out of this hole, you will need to replace the compressor rotor forward seal. If air is being sucked into the hole, you will need to replace the compressor cone seal. This is an air-to-air seal that works with the compressor rotor forward seal. Increased oil tank pressure, increased oil consumption, and white smoke coming out of the turbine exhaust can also indicate a damaged seal. If you have checked the output shaft, compressor rotor forward, and compressor cone seals, and there are still signs of a damaged oil seal, then it must be the compressor rotor aft seal or the turbine rotor seal. Since the engine must be disassembled to replace either of these seals, no further diagnosis is necessary. Both seals should be replaced at the same time to save on future maintenance. The third supporting air system is the bleed air valve. Engine surge during startup and acceleration is prevented by the bleed air valve and variable vane system. During acceleration, an increasing pressure can build in the combustor which can stop the flow of air through the compressor. The bleed air valve, mounted on top of the combustor housing, bleeds this air pressure from the combustor to reduce the pressure and to prevent surge during acceleration. As you can see in this illustration, the bleed valve is held open by a spring, allowing the excess air pressure to flow out of the combustor. The pressure inside the combustor increases with engine speed and eventually forces the bleed air valve closed. All of the air entering the combustor is now forced through turbine nozzles and rotors and out the exhaust bellows. The valve begins to close at about 152 kVA, which is about 62% engine speed, and closes completely when the pressure reaches 290 kPa, which is about 75% engine speed. Now, while this valve is a very simple device, it should be noted that it is a maintenance item requiring periodic inspection and cleaning. The major moving components in the bleed valve are the spring and piston. There are several other stationary parts, including the housing, cover, gaskets, and other hardware. Adjustments of the valve include the number of altitude shims used and the spring tension adjusting screw. The spring tension is factory adjusted and should never need adjustment in the field. The altitude shims were adjusted during commissioning by a factory representative and should not require any further adjustment by you.
Review. You have just viewed how the air system works. Let's review the important points. The PCD system supplies pressurized air to the engine gauge panel and a pneumatic signal to the fuel control valve, which adjusts the fuel pressure during operation. A running log of PCD gauge readings can help you detect deteriorating engine performance. Cooling air is routed internally through the engine to cool the combustor and turbine assemblies. The cooling air is bled for compressor. The oil seal air system prevents oil from migrating to external parts of the engine. Soft metal labyrinths are used to make the seals. Pressurized air is forced through labyrinths to form a seal against the oil. The bleed air valve works with a variable vane system to prevent engine surge during startup by bleeding air from the combustor. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check. Variable guide vane system, lesson 2. In a previous lesson, you learned that compressor can stall during the startup phase. The variable vanes move between two positions to match the air entering the compressor with the air leaving the compressor. Controlling the airflow through the compressor will prevent engine stall. When you finish this lesson, demonstrate your understanding of the materials by taking the progress check on the following performance objectives. First, describe the purpose of the variable vane system. Second, identify the two positions of the variable vanes in relation to engine speed. Third, explain the set point of the variable vanes. Here is your instructor.
The variable vanes move between two positions to control the amount of air flowing through the compressor. Engine stall is prevented by matching the amount of air entering the compressor with the amount of air leaving the compressor. This air flow is regulated by the vanes, thus preventing engine surge. There are two distinct positions for the variable vanes: the minimum open position and maximum open position. When the engine is below 66% engine speed during startup, the variable vanes are in the minimum open position, allowing a reduced amount of air to flow through the engine. As the engine speed reaches 66% speed, the vanes begin to move towards the maximum open position. This movement takes 8 to 10 seconds. The vanes are in the maximum open position when the engine reaches 100% speed, allowing air to flow through the engine at a maximum rate. The variable vane system is electrically controlled and hydraulically operated. A solenoid in the pilot-operated control valve retracts when an electrical impulse is received. Engine lube oil then flows out of the control valve to the actuator, where a piston moves the vanes to the maximum open position. The actuator piston moves a lever arm connected to 3 turnbuckles, which move an actuating ring connected to the 2 sets of variable stirrers and inlet side vanes. Let's take a closer look at the actuation sequence. An electrical impulse is received by the solenoid when the engine reaches approximately 66% speed. When the starter drops out, the solenoid retracts, causing the spool in the control valve L339 to shuttle. Lube oil pressure can now flow through the lines to the actuator. An orifice control valve restricts the flow of the oil to the actuator, delaying the flow for 8 to 10 seconds. The orifice accounts for the 8 to 10 second delay in the movement of the variable vanes to the maximum open position. Oil is prevented from bypassing the orifice by the check valve. Oil flowing from the orifice control valve enters the bottom port of the actuator, forcing the piston to the top of the cylinder and oil out of the top port. The position of the variable vanes is changed to the maximum open position. The vanes move back to the minimum open position when the engine speed is reduced below 90%. At 90% engine speed, the electrical impulse is removed from the solenoid, allowing the solenoid to extend. The spool shuttles and oil flows into the top port of the actuator, forcing the piston down. Oil flows out of the bottom port through the check valve to the oil tank. As the piston recedes, the vanes move to the minimum open position. This final movement is completed quickly to avert engine stall during shutdown. The adjustment of the variable vanes are exacting and peculiar to each engine. The correct set point angle for your engine is stenciled on the lever arm support. The maintenance and adjustment on variable vanes will be presented in a later lesson.
Review. You have just viewed how the variable vane system operates. Let's review the important points. The variable vane system partially controls the amount of air flowing through the compressor to prevent engine surge. A solenoid and hydraulic actuator control the movement of the vanes. Below 66% engine speed, the vanes are in a minimum open position. 66% engine speed, an electrical signal is sent to the pilot control valve. The solenoid changes position and pressurized oil flows to the actuator, moving the vanes to maximum open position. During shutdown, engine speed decreases below 90%, the L339 solenoid is de-energized. Oil can then flow out of the actuator, allowing the vanes to return to the minimum open position. You have just completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check. Bleed air valve maintenance. Lesson 3. The smooth startup of this engine was aided by the bleed air valve. In an earlier lesson, we described how the bleed air valve functions. During the startup, the valve bleeds air from the compressor to prevent engine surge. At 63% engine speed, the valve begins to close and all of the air is forced through the engine. The bleed air valve should receive routine maintenance out of the first 1,000-hour interval and at each additional 4,000-hour interval. This maintenance should include removing, cleaning, and inspecting the valve. When you finish this lesson, demonstrate your understanding of the material by taking the performance check on the following performance objectives. First, correctly remove and install the bleed air valve. Second, disassemble, inspect, and assemble the bleed air valve. Here is your instructor.
Job Program 1, Bleed Air Valve Maintenance. Maintenance work on the turbine package or any of its components must not proceed until the supply of fuel gas to the package is locked off at the source, the manual fuel shutoff valve. This valve must be locked off and tagged Danger. Do not operate. Always lock out the electrical starting circuits by moving the system's control switch S101 to off and tag Danger. Do not operate to prevent unexpected starting of the engine. Review the safety precautions and procedures in the operation and maintenance instructions before beginning this procedure. Routine maintenance on the bleed air valve should be scheduled after the first 1,000 hours of operation and each additional 4,000-hour interval. Now, more frequent maintenance may be needed in hostile environments. And since the valve is located on the hot section of the engine, allow time for cooling before starting this maintenance operation. Begin this operation by taping cloth around the duct which the bleed air valve is mounted on. Be sure to cover the opening in the heat blanket to keep the parts from falling inside the blanket. Remove the V-band clamp from the bleed air duct. Next, remove the 6 retain nuts and washers. The valve can now be lifted from its mounting flange. Some rocking motion may be needed to break the gasket seal. Portions of the gasket may stick to the flange and need to be scraped away. Plug the hole with a cloth to prevent debris from falling into the combustor. Remove and discard the gasket seal. Loosen the 8 bolts on the cover a little time and verify that the piston is coming out of the housing. Remember, the piston is spring-loaded and will force the cover away from the housing as the bolts are loosened. As you remove the cover gasket and discard. Carefully remove the piston from the housing. The spring seat altitude shims can now be retrieved from the housing. Remove the spring. Wash the parts thoroughly with Stoddard solvent. Do not use any abrasives. Inspect the components for damage, nicks, cracks, scoring, and evidence of binding or excessive wear. Inspect the adjustment screw for tightness. Inspect the end that contacts the spring seat for wear. Check the spring for wear in the thickness of the convolutions. If the valve has been damaged, replace it. Reassemble the valve by inserting the spring, the shims, and the spring seat into the housing. Next, install the piston by pushing it as deeply into the housing as the spring will permit. Install the cover with a new cover gasket. The bolt should be tightened in several steps to keep the cover from tilting under spring and piston pressure. Tighten a bolt at 12 o'clock and another at 6 o'clock. Finally, torque the bolts to 25.4 to 29.9 Newton meters. Install a new gasket on the body's mounting flange studs. Next, seat the valve on the mounting flange. You will have to raise the valve slightly to replace the nuts and washers on the studs. Tighten a nut and then its opposite, as you did with the cover. Finally, torque the nuts to 47.4 to 67.7 Newton meters. Install the bleed air duct and the V-clamp. Torque to 5.75 Newton meters. The package should now be started to verify proper operation, smooth acceleration, and temperature stabilization. The maintenance procedures in this job program may omit some of the connections or disconnections of certain fittings. When you are doing this maintenance program on your package, you must ensure that all fittings and connections are secure before operating the equipment. Always refer to the operation and maintenance instructions for details.
Variable vane maintenance. Lesson 4. This engine is running at 100% speed and is forcing approximately 17 kilograms of air through it a second. During the startup, the flow of this air is determined by the angle and position of the variable vane system. The vane angle adjustments are exacting and peculiar to each individual engine. The adjustment of the vanes is the central focus of this lesson. When you have finished this lesson, demonstrate your understanding of the material, taking the performance check on the following performance objective. Correctly measure variable guide vane angles and adjust to specifications. Here is your instructor.
Job Program 2, Variable Guide Vane Adjustment. Review the safety precautions in the operation and maintenance instructions before beginning this procedure. The position of the variable guide vane should be checked after any maintenance procedure has been performed that could change their positions, and after the first 1,000 hours of operation, and after each additional 4,000 hours of operation. Remove the bolts and sheet metal enclosures from around the variable guide vanes. Inspect the assembly for contamination and loose parts. Make sure that all of the components are securely tightened. Next, remove 2 bolts from the air inlet housing for the gauge. Now the gauge can be installed over the scales. Begin by placing the gauge over studs and tightening the bolts finger tight. Bisect this hole with the upper face of the gauge. Make any necessary alignment adjustments with the gauge and make certain that the dowel pins are resting on the lip of the air inlet housing. Tighten the 2 nuts to hold the gauge in place. Again, check that the dowel pins are resting on the lip and that the edge of the gauge still bisects the hole. Start the engine, and while the speed is below 66%, check the position of the vane. The scale should read -35 degrees or C on the inlet scale, -29 degrees on the first stage stator scale, and minus 24 degrees on the second stage stator scale. If there is a deviation in the specifications, check the position of the tool over the center hole of the inlet guide vane pivot shaft. If the tool's alignment is correct, the vanes must be adjusted. When the engine is running at 100% speed, the variable vane should be completely open. The reading on the inlet guide vane scale should correspond to the angle stenciled on the lever arm support housing. Shut the engine down. As the engine falls below 90% speed, you should be able to observe the movement of the variable vanes to the minimum open position. Again, the machined edge of the gauge should be in alignment with the minus 35 degree or C, minus 29 degrees, and minus 24 degrees on the guide vanes. Adjustment of the variable guide vanes is made when the engine is shut down and properly secured. To make the adjustment of the vanes, disconnect the two lines to the actuator. Connect a source of oil pressure of 380 kPa to the top port of the actuator and secure it. Next, attach a drain leading to a bucket to the bottom port and secure it. Now pressurize the actuator and drive it to the fully retracted position. Set the inlet guide vane ring to minus 35 degrees or C by adjusting the turnbuckle from the ring to the lever arm. Loosen the turnbuckle locking nuts. Then adjust turnbuckle. Tighten the locking nuts. After you have turned the oil pressure off, reverse the position of the two oil lines leading to the actuator. Drive the vanes to the fully extended position. The reading on the scale of the inlet guide vane should correspond with the stencil setting on the housing. If the scale does not match the indicated reading, the lever arm turnbuckle must be adjusted. Adjust the turnbuckle so that the scale reading matches the stenciled reading. Shut off the oil pressure and reverse the oil lines. Pressurize the actuator and retract the vanes. The inlet scale should read minus 35 degrees or C. If it does not, adjust turnbuckle from the ring to the lever arm again. Then reverse the oil lines again and check the maximum open position. Additional adjustments may be necessary to achieve both settings. Reverse the oil line and retract the vanes. When you have adjusted the inlet scale to read minus 35 degrees or C and have matched the stenciled reading, check the reading of the first and second stage support rings. They should read minus 29 degrees and minus 24 degrees respectively with the actuator retracted. The first and second stage stators can be adjusted by rotating the turnbuckles. After you have made all adjustments, tighten locking nuts on the turnbuckles. Make sure that each turnbuckle will rotate freely on its bearings. Retract the actuator and turn off the oil supply. The pressure lines can now be removed and replaced with the actuator lines. Torque the securing nuts to 9 to 13.5 Newton meters. Next, remove the gauge and replace the two nuts. Torque the nuts to 24 to 30 Newton meters. Carefully replace the housing cover. Tighten the bolts finger tight to allow enough play to insert all of the bolts. Torque the bolts to 8 to 9.6 Newton meters. The maintenance procedures in this job program may omit some of the connections or disconnections of certain fittings. When you are doing this maintenance program on your package, you must ensure that all fittings and connections are secure before operating the equipment. Always refer to the operation and maintenance instruction for details.